We will talk about reinforcement learning. Whether you have heard about this word, this concept of reinforcement learning or not, I believe you have heard about the other concept like artificial intelligence or AI, right? Because they have been in the news so much over the last few years. So the concept the concept artificial intelligence had been around actually since the 1950s, right? So it has had a lot of up and downs over the years. In recent years, it got popular again, or say very popular, mainly due to the success of two sets of tools, right? So one is deep learning, basically deep neural network model. The other is reinforcement learning. And certainly a lot of time they also utilize it together. Deep learning, we know, have found a lot of success in things like image recognition or language processing, right? Reinforcement learning, on the other hand, I guess, at least myself, probably most of people started to pay attention to this probably around 2015. Around that time, there was a company called DeepMind, later acquired by Google. And they pretty successfully played the game Go with some computer program. It won a lot of games against all the best human player in the world, right? Because game Go was considered a very, very challenging problem to solve for the computer. So it was considered a breakthrough after that. Clearly, the tool has attracted a lot of attention, a lot of investment fundings, and become an extremely active research area for academia and some research lab in the industry. Of course, with all this research, we're finding more and more applications as well. So what we are going to talk about today, obviously, is its application in marketing. We'll see how this can help. So this title here is called Salesmanship Enabled Martech. If this title feels strange to you, that's entirely not surprising, right? Because it's pretty much me who made this up. But it's not new, right? Concept is not completely new because it has something to do with my experience in advertising before. Advertising is sort of one of the things, everybody has seen it. To a degree, you probably think it too much already and you got annoyed, right? On the other hand, if somebody come to you and say, what is advertising? How do you define it? Is probably actually not a very easy question to answer, right? And turns out more than 100 years ago, there was a very smart guy, probably one of the best minds in the history of advertising. This guy actually said something that advertising is salesmanship in print. Of course, more than 100 years ago, you can imagine print was the only major form of mass media at the time. Today, we can probably call advertising the salesmanship in TV, digital, social, and print, radio, all this different media we constantly consume every day. Now, this is not just an interesting definition. It also kind of provides some guidance about how we generally should think about advertising, or to a larger extent, or the different marketing activity. So if we think about how a good salesperson will actually talk to a customer or a prospect, a good salesperson at least will treat the customer communication as an interactive process, right? Interaction means a two-way flow of influence. So the salesperson might say something to the customer, and the customer might change his or her mind. Then in return, probably will give some sort of signal, maybe implicit and maybe explicit, right? Give some signal to the salesperson. The salesperson will have to, change his communication strategy accordingly, right? Basically, this is supposed to be a dynamic process. The other thing in our context, we can say a good salesperson will focus on the final price, right? Which is actually win the customer. We probably all have this experience. Let's say we go to a store. If you feel somebody was so desperate trying to sell you something, a lot of suspicion will probably be raised in whatever conversation you might have, right? So sometimes we just need to realize in order to achieve long-term goal, we have to make some short-term sacrifice, right? Because the salesperson need to recognize you don't have to win every single conversation or exchange you have with the customer. It might take multiple steps to actually convert somebody, right? So focus on the final price, to focus on long-term impact, or say the cumulative effect of all your communication, possible communication with the customer. Basically, in our context, we think this two might be pretty important, right? let's take a look at some example, how in the marketing industry, how we have been leveraging all the different marketing analytics tools or analytics modeling, how we have been leveraging these tools in engaging customers. And then we can see how reinforcement learning can potentially help us to improve on some of these tasks. So the first example here, I guess a lot of people probably already recognize this, right? So this is very common in marketing. Say we know some information about the user, and we want to predict something. Sometimes there's a customer the likelihood to convert, whatever conversion actually mean in your context, right? And there are also other times we want to predict something like a customer lifetime value by using this kind of information. This is all predictive modeling or supervised learning kind of model we used a lot in the past, right? Now, what might be the problem in here? Think about typically, let's say we are running a direct mail campaign. We want to predict who is going to convert, right? And in those scenarios, typically, we are not thinking about what will happen after this direct mail campaign, right? We only focus on whether people will actually respond to this particular campaign or not. So basically the focus is the immediate impact. Now, on the other hand, customer lifetime value, it's called lifetime, obviously is considering some kind of long-term effect. But when we do that, again, if let's say you acquire a new customer, the customer come in, the business is not going to just sit there wait for the customer to buy, right? You will do a lot of engagement, retention effort with the customer. But when we build this kind of model, typically we are not taking those retention effort into account, right? Essentially, we are thinking of the customer as a static entity. We just assume everything will stay the same and what will be the lifetime value. So then a common problem for both of this, again, in the way we just described, typically there might be some sort of action, right? Some kind of a stimuli. You want to see the impact of the action on the customer. Let's say if you have, every major brand will run many marketing campaigns, spend billions of dollars every year, right? And many different action, many different marketing campaign. And when you try to build this type of model, essentially for each different type of action, you need to build a separate model, right? And think about if you have lots of them, then you need to build many models. It's quite, it's very hard to make it scalable. And as a matter of fact, typically when people build this kind of model, it's more probably for the purpose of segmentation or basically shorten the list. Let's say we have millions of prospects. We do not have the resource to target everybody. We just build this model and take whoever on the top and focus our resource on those, right? So that's typically how people use this kind of model. But we understand there are other scenarios. For example, if you have an e-commerce website or if you go to Netflix, there are millions of product or whatever item the website want you to interact with, right? And every page we as a user visit on the website, the company will show us some related, probably in some way related item, and hope will like that and further engage with them, right? So basically, this is the personalized recommendation, or sometimes the people call this next best action, right? So it's a very large scale problem typically because you might have a lot of users. You might have a lot of items on your website. Sometimes the millions of users, millions of items. You will get a very large matrix like this. Very large problem. That kind of solves the problem we mentioned earlier about this, one model per action approach. However, when we go to a website, right? When the website shows us the related items, what the algorithm was thinking or trying to optimize is really whether we will click that particular recommendation, right? Think about, when we go to a website, we will interact with the website for a few different steps. You might stay there for quite a while and navigate around and browse different pages, right? So when the algorithm make a particular recommendation on a particular page, it's not thinking about how you will further engage for the remaining interaction you might have with the website, right? So that's sort of one of the disadvantage, in the context we just mentioned, how we should engage with the customer. If we can make an analogy, let's say we are playing a game. By the way, this is kind of the poster for this documentary called AlphaGo. Earlier we mentioned a lot of people start to pay attention to reinforcement learning because DeepMind played successfully the game Go, right? So Netflix actually made a documentary and tried to dramatize the whole thing. And if you're interested, can go there, take a look, right? But in our context, think about if we are playing a game, whether it's chess, it's Go, or even playing like a ping pong. It involves a lot of different steps. When we try to play this, typically we want to focus on the goal of winning the game. We probably don't have time or not quite necessary to think about whether we can win each step. And there's a old Chinese saying, I'm from China. People typically say when you play chess, right, play this game, you need to think at least 3 steps ahead when you try to take 1 step, right? So basically, the how do you balance the short-term goal and the long-term goal? That type of thing. The last example I want to mention here is basically multi-touch attribution. So the first 2 examples are essentially in the category of marketing execution, right? How do you help people to take action? Now, multi-touch attribution happen afterwards, right? So after the campaign is run, it's for measurement purpose. A user might have been exposed to multiple advertising or multiple marketing activity, and eventually, let's say, it purchased something. Basically, the question MTA is trying to answer is where the credit should go. A few years ago, I was doing MTA. We talk a lot to the client, and a lot of the client clearly not technical, but they typically have a pretty good sense about how advertising should work. Some client always ask this type of question, right? So now you're telling me what advertising has worked, what didn't, but can you tell me whether you can take the synergy of all the different ads into account? The synergy in our technical term, basically the interaction effect among the different advertising, right? Or another question is like, can you tell me what might be the best sequencing to run all these different ads and show them to the different user? If you really think about this, it's actually pretty hard based on the traditional tool we have. Yes, in MTA, we focus on user level data. Theoretically, we have a lot of data. But when you try to think about the sequence, you will quickly see the number of users behind each of the sequence is actually will quickly become very small, right? So it's become a very difficult and challenging problem. All in all, right? So the point we're trying to make here is a lot of the traditional marketing analytics we do typically focus on the immediate impact, right? Or treat the user as a static, not a dynamic, not treat the marketing communication process as a dynamic or interactive process, and sometimes also not to focus on long-term goal, right, as we should be. So now let's take a look at. We said quite a lot about what the disadvantage might be. Let's take a look at how reinforceable learning in this framework, how we can view the engagement process with the customer. As we know, right, we built a lot of different models in the past. Whenever we try to leverage some model to solve a business problem, we have to first convert that business problem into the statistical framework or the mathematical framework we are familiar with, right? Then after we put them into that framework, we can use the statistical tool or the math tool to solve this problem. And in terms of reinforceable learning, will look at the world as MDP, okay? A Markov decision process. I just highlight the word decision here, right? It's a process, it's a decision process. On the previous page, we said we can predict the likelihood, we can predict lifetime value. Here, the output from reinforceable learning is basically the action, directly the action you are going to take. Okay, so that's why it's called a decision process. So in this framework, there are 2 very important roles. One, in technical term, one is the environment, the other is the agent. Okay, in our marketing context, we can think of the environment as the customer. Okay, and the agent is basically working on behalf of us, right, the marketer or the advertiser. And the agent can take action. The action are basically all the different marketing tools we have, or the advertising we have, right? So before the agent take action, the agent might know some information about the customer, in this technical framework, we'll call that the state or the status of the customer, say the profile of the customer, right, the state. And based on that information, the agent will take an action. The customer, in response, will give some kind of reward. By the way, the reward is a very generic term here. It could be positive, it could be negative, right? So, for example, if we care about the market, if we care about the revenue, we just focus on the purchase the customer actually made. But certainly there are also costs with all the different marketing activity. So if the customer does not buy, it might be just a negative signal, right? And in the meantime, the customer, like we said earlier, might also change its status, right? Mindset might change, whatever, right? So then all this data will go back to the agent, and the agent will take them into account to further refine its strategy to interact with the customer. So in the end, what we observe from this process are basically all these different sequences. Remember on the last page we showed traditionally with supervised learning, we are thinking about all this data matrix, right? Here, it basically becomes a sequence or say a trajectory episode in technical term, right? So essentially we know something about the customer, which is the state, then the agent will take some action, you get some reward, and the consumer will change it to a different status, then you take a further action, get further reward, all that stuff. This will repeat itself, and you might get some pretty long trajectory. And the agent's job is basically figure out a policy for us to take action considering the state of the customer, right? And the goal here, the goal of the policy is to maximize the cumulative reward, right? The reward you get from each different step, but take a longer term view. At each step, I will take a longer term view, thinking about not this step, this action will not just benefit my current step, will actually benefit me long term, right? So that's kind of the difference between reinforcement learning and the traditional supervised learning model we built. I just want to quickly mention, right? So this is the framework for reinforcement learning. It's not completely different from supervised learning. As a matter of fact, supervised learning can be considered as a special case of reinforcement learning. Okay, basically reinforcement learning is a more broader concept. It's a broader concept than supervised learning. If we think about how, we can think about it this way. Let's say we are building a likelihood to convert type of model, right? Let's say we are doing that with a logistic regression. Basically, the agent is equipped with a logistic regression, and you will get some probability about the conversion. And based on that probability, we can say whether the user is going to convert or not. Then we will observe the customer actually convert or not, right? And then if what we said about the likelihood is correct, then the agent gets some positive reward. Otherwise, you get 0 or get no reward, get some negative reward, right? So in that case, and if we think of the logistic regression or the supervised learning model in that way, this is clearly a special case of reinforcement learning. So it won't be surprising. You will see the optimization method or the different setup we have to do for reinforcement learning can be more complicated than supervised learning. Actually, supervised learning typically are used as the building blocks to train a reinforcement learning model.
I have a question. Sorry.
Sure, no problem. Go ahead.
When you describe the states, actually here, you assume the states are known, not like so-called, so the customer profile clearly define the state.
Yeah, right? That's actually a great question. I actually simplify this a lot. In the technical literature, you will see some different terms. There are some distinction with them. The first term you might see the history. The other is the state, right? History basically means everything that have happened, whether we as a market actually observed or not.
But,
right?
even history, actually, think of this way, even the history, actually, you don't have a full observation, right?
Correct. Yeah, that's what I'm saying, right? History is what actually happened, whether we actually observe it or not. State basically means what we know. That might be part of the history, or might be some kind of transformation of the history.
What it means, like a state should be clearly defined, but actually with certain probability, the customers in a certain state, but that's only in probability. It's not decisively.
I mean, that probably become more complicated question. Think about this way, right? Let's say on the previous page, we give some example. You can think of state as all the information we actually know about the customer. Obviously, our data is never complete, right? For every project, we probably only know partial information about the customer. So that's why this process, typically the statistical or stochastic process, is typically not deterministic, right? Because the data we know is not complete, right? But the thing what we can do, it's kind of like in supervised learning, right? We take advantage of the data as much as we can. For the stuff we cannot observe, it can only be assumed as a part of the noise or the randomness in the process.
But here, I mean, there are two kinds of randomness. One is like from state T to state T plus 1.
Correct.
It's randomness. Another one is the state itself is random because you don't know it exactly in certain state or not.
Again, right? So we are saying this is state in our context is basically what we actually know, right? If you say there's something we don't know, and maybe we can model that like what you said, model that as some distribution. That's possible, right? But this is the input. This is supposed to be the input to the model.
Oh, okay.
Right? Even in supervised learning, for example, there are a lot of stuff we don't know about the customer. Right? It's the same thing.
Here's a comparison with like the game Go. The state is clear. You know exactly what happened. What is the situation now? You know exactly. But for the customer, you only know the customer didn't buy certain thing, but you don't know whether the customer already bought from other places, right?
Yeah. That's a brilliant observation. Actually, if you go into the technical literature, again, we are simplifying a lot.
Yeah, sure. I just want to point out the state is actually a probability instead of is for sure.
Yes, a lot of the time that we don't have full information. That's correct. We can only do things based on what we have. And the other thing, like you mentioned a game ago, we know everything. MDP, if you go there, typically we are handling some partially observed MDP, right? In our case, it's a partially observed MDP, not a full MDP. If you know the full MDP, it becomes like a model-based. There are a lot of technical terms just to describe what you just mentioned, right? So it's each term you just mentioned, each scenario you just observed, you just mentioned can be an hour-long, a days-long kind of conversation. Yeah.
Okay.
So, cool.
Good. Thank you.
Yeah. The other thing you mentioned, like the transition. Let's say we mentioned like state or reward. A lot of this thing actually modeled as stochastic. Let's say the first one is the transition from one state to another. It might be probabilistic, stochastic. The other thing is the reward might also be probabilistic. Right? It's not deterministic. So there are a lot of flexibility in this. Cool. So we're having some very good conversation actually. So this is the framework, right? How we look at things. The next thing we should consider is how we actually train an agent, so the agent can do things on our own behalf, right? The math, right? The math is always confusing and complicated. But if we really extract the main idea behind all this algorithm, is actually quite common sense. You will see it's actually no more than what we have learned probably from elementary school, right? Over the past few days, I've seen a lot of people actually have been having fun with this video on LinkedIn. So I just put it here. It's a pretty short video. If you look at this, you will know what I mean. This thing is actually pretty elementary. Let's take a look at this. So there are actually several different versions of this video, right? Just made by different people. I saw a couple actually all using chicken for some reason. Might be maybe the case chicken actually pretty smart. Okay, so as you can see, right, the idea is actually pretty straightforward. If we can think of the chicken, think of this scenario in the framework we just talked about. The chicken here is actually our agent, right? And the action that a chicken can take are all the different, the action it can take is basically touch on different color. And the reward it get, basically when it touch that pink color, the chicken will get some reward, get some food to eat. Right, so it's basically this framework, and the chicken will follow the reward and eventually figure out by taking what action it might get a reward, basically solve this reinforcement learning problem, right? So that's basically the process of solve this. But if you pay attention to what I was saying closely, I kind of ignored one of the components in this framework we just mentioned, basically what Zid was talking about earlier, the state, right? We didn't say anything about the state. Essentially, in this framework, it's a very much simplified reinforcement learning scenario in which there's no concept of the state. All you can say, the state doesn't matter, right? No matter in what state, the reward you can get from each action always stay the same. Right? Basically, whatever action you take right now, it had no impact on the future. Right? So this is actually called a one-step MDP, not because in a multiple-step MDP, you have to think about the future. Right here, you just think about the current step. And the one-step MDP is simplified, but it actually have some close connection to something we know very well, which is basically A/B testing. Right, so A/B testing, the difference, I guess, is in A/B testing. Let's say you have different option, you can randomly put the user into a different group, show them this action. You wait, right, and then until you get enough sample size, you learn which is your best action. Then you will take action from there on, right? So essentially, it's kind of like you first explore. Then try to exploit, right? Essentially, you first learn, then try to apply them. Now here is, this thing is called multi-armed bandit. Essentially, it's an online learning paradigm. You exploit your knowledge while you are exploring. Essentially, kind of like you learn while you are working, or say if you want to learn swimming, just jump into the water. A different type of approach, right? So the benefit essentially is, in A/B testing, you have to wait, right? So whatever you do in the waiting period, you basically wasting your resource. Now here is at the online learning, you basically try to balance the task of exploitation and exploration. So then you can gain more reward essentially. Okay, so that's kind of the difference. However, if we ask a very simple question, let's say we change the setting a little bit. This two girls, let's say, instead of giving a reward when the chicken touch the pink, let's say we predetermine two different colors, let's say a blue and a pink. If the chicken first touch on the blue, then touch the pink in a row, then we'll triple the reward to the chicken. Right? In this scenario, think about the state actually matter. Right? Because so when you first touch blue, you do not get anything. But if you keep going, then touch the pink, you will get some. You get multiple reward, right? So essentially, you have to take the sequencing, the ordering, or the interaction of the different action into account, right? So that's get closer to a real reinforcement learning problem. But the idea to solve this, and again, it can be complicated, but the core idea, just think quite intuitive. Let's say if we can build a model to predict the long-term value we can actually get from each of this state action pair, then at any given point, we see a state, we see a particular customer, we just follow this so-called value function, right, which help us determine the long-term value. We just follow this value function and in a greedy way, pick the action that give us the highest score, then go with it, right? That's basically the idea. That's from the foundational idea of solving reinforcement learning problem. But certainly, if we come back to what we said earlier, right? So the core idea is intuitive, but the math is indeed is actually quite complicated and confusing, right? So many smart people have been trying to work on this. Many algorithms have been created, and this is sort of a taxonomy, but it's nowhere near a complete list, right? So the other thing obviously we would not get into too much detail about this, but the other thing we want to quickly mention, we mentioned earlier deep learning and reinforcement learning. We also mentioned a lot of the time the reinforcement learning algorithm are built on top of deep learning, right? So when that happens, this is called deep reinforcement learning. So if you see this term, it's not quite hopefully it's not as confusing as before, right? The other thing we can quickly say is there are algorithms. Think about in supervised learning, we also have a lot of algorithm. And on the other hand, we have a lot of package, R package, Python library, all that stuff. And people have also been trying to develop packages for reinforcement learning. This is, at least some people, this is basically some just open source project. People are developing this, right? But I just want to give everybody a heads up. This thing is not as mature as what we can see from supervised learning. You probably need some pretty good technical background in order to engage with this right now. Okay, but there's some link here if you are interested, and feel free to take a look afterwards. So we talked about what the algorithm should like, right? We talked about the framework, like what the algorithm should look like, and the different tools. But we, as somebody who built a model before, we understand modeling is not just to find an algorithm and feed your data into it, right? It's actually a pretty long process. So if we, from a high level, if we divide this into 3 stages, right? Data preparation, then you run your algorithm, eventually do testing, right? And we mentioned earlier, reinforcement learning inherently will be more complicated than building a supervised learning model. There are more factors that you have to take into account, right? For example, when you prepare data, and how do you define your state? How do you define your action? How do you define your reward? That also, you probably need to take into account the kind of business problem you are trying to solve and the data you have available, right? And design this and find the right algorithm for yourself to use, eventually do some testing. We won't get into the detail, but I just want to quickly mention, for testing in reinforcement learning is sort of a counterfactual problem, right? Think about, let's say we are doing a supervised learning problem. We have a bunch of pictures for dog and cat. We build a model to tell them apart. And if you want to do testing, you basically find a new picture of a dog and feed them into the model. Let the model tell you whether it's a dog or a cat, right? It's pretty straightforward. But in reinforcement learning, think about what the policy is trying to recommend is a sequence of actions. And it's very possible this sequence never exists in the historical data you have. Essentially, reinforcement learning is not just trying to mimic what you have in the data, it's trying to improve or optimize, right? That's where it makes things complicated. So it's counterfactual, and it requires some kind of probability calculation in order to figure out whether the algorithm is performing or not. We won't get into detail, but just give everybody a heads up. So there's some difficulty here. The other thing, we will be very quick on this. Essentially, let's say if we want to make reinforcement learning actually practical for the business world, right? We understand it's a long process for every major project we do. Every project start and end with the business. Anywhere you have to interact or take into account the business reality, that's the part where it's hard to actually automate, right? And the stuff in the middle, the algorithm, all that stuff, it's complicated, but actually the part that's easier to automate, right? Eventually, this supposedly pretty large project, and a lot of stuff need to come together. Like the business, we need to have a pretty good understanding of the business, and the data, the model, the computational platform, even the law, right? Right now, there are a lot of conversation about the privacy, all that stuff, right? So we need to, we in the context that we are talking about, we're thinking a lot about user level data. So we have to think about that, really think about that ahead. But eventually, no matter what we do. The goal is to deliver some incremental value to your business, right? That's the foundation for everything. So we have a few minutes left. I just want to quickly show you some demo, right? So we talk a lot of theory. I just want to give you a demo to see how well this thing can actually perform, right? This demo is fairly complicated, I would say. It's a simulated data. In the simulation, there are basically two components. The first component is obviously the algorithm to train the agent. The other component of the simulation is a simulator essentially simulate how a customer will make a purchase decision, right? Then we will let the agent, the algorithm, to interact with the simulator of the customer, see whether the agent can actually figure out whether it can send the right message to the right people at the right time, right? So I wouldn't get into too much details. If anybody interested, we can certainly have another conversation offline. We basically take into account quite a few different factors that can affect people's shopping decision, like demographic, past shopping frequency, or past purchase amount, and also the impact of advertising. In terms of advertising, we take into account like half-life, diminishing return, and also things like purchase cycle, right? We're assuming towards the end of the purchase cycle, the advertising will have a bigger impact than the other part of the purchase cycle. Okay, so let me just go to this notebook so we can take a quick look, just to give everybody some quick sense how this is working, right? So in the simulation, I basically simulated 5,000 different customers. They are split into 18 different segments, okay? And this 18 different segments, it has a hierarchy, right? The first hierarchy, there are 6 segments. Their purchase probability will be different, right? But once we have the purchase probability, the simulator will basically run a binomial distribution or a binomial distribution, determine whether the customer will actually buy or not. If it's a buy, it will leverage another variable to determine how many the customer is going to buy, right? So there are 6 different group of customer. They will have different purchase probability, and the impact of advertising on them will be different. You can see I simulated 8 different ads, basically 8 different action plus no ad. Okay, no ad, no action is also a part of action, right? You can see for each of these 6 group of customer, their impact to the customer's purchase probability will be different. Okay, very quickly, I just want to, we want to get through this. And the other thing before I show you the result is, in addition to say advertising will have a different impact on the consumer's purchase probability, I also assume different advertising has different advertising has different cost. Okay, so essentially the agent will be trying to balance between the benefit of the advertising and the cost of the advertising, because the goal I set for the agent is to optimize the total reward, which is basically the purchase amount minus the cost of the ad. Okay, so let's say if you send an ad to a customer, it can drive up the probability, and the cost of the ad is 3 cents, let's say. And the customer is going to, typically when it buy 1 unit of the product, the price of the product is assumed to be $1.50, right? So if the agent determines the ad can drive the purchase probability up for more than 2%, then the expected outcome could be more than 3 cents. Then supposedly the agent will send this ad to the customer. Otherwise, it shouldn't do that, right? So that's roughly the idea, the kind of work that the agent should do. As you can see here, we just mentioned we have 9 different action, right? 8 different ads plus no action, and the x-axis here is basically the number of days in the purchase cycle, okay, from 0 to 30 something days, okay? And the red color here means no ad for those days, right? Let's go to the bottom, we can see the number of days here, right? You can see for each group of customers, we have 18 different segments, right? And for each of this group, pretty much every group, and at the beginning of the purchase cycle, the agent always determine there's no need to send ad to these people because we mentioned earlier, there's a purchase cycle effect. Toward the end of the purchase cycle, the ad will have a bigger impact. Okay, so the agent figure that out and only send the ad to the customer at the end of the purchase cycle, and also in different kind of sequence for different user segment, because different ad has different impact on the customer. The agent is trying to maximize the cumulative reward by taking a longer term view how to interact with the customer. Okay, there's a different sequence here. Now, the outcome here, let's take a look, right? So we trained an agent. Here we will call them the actor. We will show how many ads on average the agent actually sent to each group of customer, right? We have 18 group of customer again. So at the benchmark, I also include some pretty dumb benchmark here. Let's say no ad at all. You don't interact with the customer, wait for them to buy, right? And the random ad, because we have 8 ads, right? You randomly select 1 ad every day, send them to the customer. And the other is you just take a random action because there's no action as 1 action, right? So when you do random ad, you can see, by the way, the episode I'm using is, we are assuming the campaign period is 183 days, right? You can see if you do random ads, you send 1 ad to the customer every day. You basically on average show 183 ads. And the random action also show a lot of ads to different people. The actor, the no ad obviously means 0. And the blue bar here shows what our agent has been doing, right? It clearly figured something out, and it didn't quite show a lot of ads to different groups. Actually made some distinction among different groups. For example, the first group here is the group with the lowest purchase probability. The agents almost gave up, right? Didn't do much. And for the group with a heavy equal to 2, that basically means the customer who are going to buy a lot. Then it actually showed quite a few ads to those people, right? Then let's take a look at the, I will skip this one, just take a look at the actual purchase amount from different group of customer, right? Under the simulation, you can see people actually make a different amount of purchase, right? And under the influence of a different agent, their behavior are also different. So, but the blue bar, right? Again, this is the actor. Even though it didn't send a lot of ads as the other agents do, it still stimulates the most of the purchase for most of the user segment. Let's say for this one, because the agent almost gave up, so the customer didn't buy much. However, like we said earlier, we want the agent to balance the cost and the benefit, right? So see here, even though the customer didn't buy much, but your gain is still positive. And the other agent, because it's sending a lot of ads to the customer, even though they purchase something, the total reward is actually negative, right? Then for the other group, you can see the trained agents clearly outperform all the other different agents. Okay, so I just will, obviously we have limited time. We'll go through this very quickly. And I think this is probably the last slide in terms of the main material. We mentioned the MTA earlier, right? People have been asking, in doing MTA, is it possible you can take into account the synergy or the sequencing effect of the different ads, right? And so if we, again, need to put this into a rigorous framework, we should say MTA is trying to figure out the incremental value the advertising actually generates. Right? Again, what is the incremental value? That's sort of like advertising. Everybody talk about it, but hard to define, right? So there are different theoretical framework in statistics, in game theory. We won't get into them, but the core concept essentially is the marginal value, right? So the value you can get with that minus the value you can get without that. That can be a good definition of incremental value. Okay, and we mentioned the word value. You probably recall we mentioned something like a value function earlier. And so basically, this MTA can be sort of a byproduct of training a reinforceable learning model. So you can leverage the value function you actually get in the training process for your measurement purpose as well. So those are all the framework, right? In terms of data, if you are thinking about trying something like this by yourself, And typically the kind of data we need, essentially you need some kind of data sets that help you to establish the communication history, the interaction history between your business and the customer, right? And obviously you need the behavior data. You need to know what kind of advertising or marketing the customer has been exposed to, and in return, what kind of response or conversion you have seen from them. And certainly some other metadata can also help, like the customer profile, whatever you know about the customer, right? Let's say demographic or that stuff. And also the profile about your product, might be product hierarchy, color, weight, price, or those things. And all this come together, help you to establish the history of interaction, basically generate all those communication trajectory we mentioned earlier. Then you can leverage the algorithm to figure out what's the best way to interact with the customer. Okay, so here, this is just for fun, just saying data is never perfect, right? So again, just I've been doing this for doing marketing, different kind of marketing analytics for over 10 years. I don't believe there have been a single time I think a data set immediately say we can build a model. There's always a problem in data, right? But again, our job or the algorithm's job is trying to figure out or extract as much information as we can from the algorithm. Not to say we can generate the information, right? We try to take advantage of the data we actually have. Okay, so in conclusion, right? This will be very short. I hope we came across this story came across and just saying reinforcement learning can really help us to engage the customer in a orchestrated way, right? We'll treat this as a more dynamic, interactive process, and by focusing on the long-term or the cumulative effect of the different marketing activity you might have. And by leveraging deep learning, reinforcement learning, basically the deeper reinforcement learning, we can also make this scalable. And certainly there are a lot of different concepts in marketing, like different targeting, personalization. In recent years, people talk about the journey of attrition and even marketing, major marketing effectiveness measurement like MTA. And potentially we can see application of reinforcement learning along all this line.